G'day everyone, and welcome to our lesson on the photoelectric effect example questions. A quick summary of the apparatus used in the photoelectric effect. First of all, you have a battery or some kind of voltage source here which you can vary. Then you have a metal sheet here, a receiver electrode. Then you have an ammeter to measure current. And finally, it's good to have a voltmeter across here, so you can tell how many volts are going across that power source, and therefore the amount of voltage that's going across this gap here. You also have a light source. I'll draw it down here, which shines photons onto that metal surface there, which causes electrons to be ejected. If you place different coloured screens in front of this light source here, if that's a white light, you can actually manipulate the colour of the light hitting the screen, and therefore the frequency of light hitting that screen there. What we're going to do is look at experimental results here and use them to deduce the threshold frequency, the work function, and our experimental value of Planck's constant. Now recall, Planck's constant when given in electron volt seconds is 4.14 times 10 neg 15 electron volt seconds. This is the value given to you, which you should always use, but in this experiment we're hopefully going to find a value that's similar to this by using these data points here. So recognize that the relationship between the energy here, this is the kinetic energy of the electrons, is given by Planck's constant multiplied by the frequency of light, take away the work function. This looks a lot like y equals mx take c, because the work function is constant, m, the gradient, or h is constant. So we're going to expect some kind of straight line if we're graphing kinetic energy, which is y, against frequency, which is x here. So looking to the graph I have to the left, vertical axes can be the kinetic energy of the electron in electron volts, and the horizontal axes can be the frequency in hertz. Let's start marking in our data points. I mark them in with a fine pen. So the first one we have 4 times 10 to the power of 14, so 4e plus 14 means 4 times 10 to the power of 14. That's the frequency of light we shone upon the metal surface down here. Oops. And we had an electron ejected of energy 0.1 electron volts. So moving over to our graph over here, we find this is 1 times 10 to the 14, 2 times 10 to the 14, 3 times 10 to the 14, that's 4 times 10 to the 14. And the energy is 0.1. It's halfway between the red line and the first black line. So I'm going to mark that in there. That's our first data point. The second data point occurs at 5 times 10 to the 14. Well, that's easy, it's marked in. And we have an electron ejected of energy 0.5 electron volts. So I can mark that point in there. Then 6.5 times 10 to the 14 and 1.1. Well, that's 6, so this is 6.5. And 1.1 will be halfway between this line and this line here. I'll mark that data point in there. Then we have 7 times 10 to the 7.1 times 10 to the 14 and 1.34. Getting a little difficult, so 5, 6, 7, 7.1, perhaps somewhere there. And we have a 1.34. So that's 1, 1.1, 1.2, 1.3, 1.34. There we go. And looking back, I think the data point, back there was a little bit this one. I think this one should have been a little bit over that way, but we'll ignore that for now. Final data point, 7.8 times 10 to the 14 hertz light incoming upon that metal surface down below. And we have an electron ejected of 1.62 electron volts. So I'm going to mark that in 7.8, 5, 6, 7, 7.8, 1.62. Somewhere there. And we do get a straight line, which is what we wanted. And that's saying that the energy of the electron is probably equal to some kind of gradient multiplied by the horizontal axis, which is F, take away the work function there, and there is a definite shift down. So we're actually going to connect these points together with a line of best fit. So I'm going to try and collect as many of those points as possible. That looks pretty good. And then I'll draw that line in. Even though we can't actually have negative kinetic energy electrons, I'm still going to mark that line in below the horizontal axis because it comes into use later. And then we have a straight line there. Okay, the first question asks us, what is the threshold frequency? And this means what is the lowest frequency of light that ejects an electron? How low can we make the frequency before we see no electrons being ejected from the metal? Now we saw when we shone light of 4 times 10 to the 14 hertz upon that metal surface, we had an electron ejected of 0.1 electron volts. That's almost nothing. So we expect that if we lower the frequency a little more, we'll get an energy of 0 electron volts, which means the electron has made it off the metal, but just by the skin of its teeth. It has no kinetic energy left. And so we look down here, where does this black line intercept the horizontal axis? I'd say if this is 4 times 10 to the 14, this must be 3.8 times 10 to the 14. So the threshold frequency is around 3.8 times 10 to the 14 hertz. Notice this is all done with our experimental results, not reverting to this formula up here quite yet. The work function, we'll find it experimentally the same way. The magnitude of the work function is actually given by the intersection of this black line with the vertical axis here. You can tell if we add the line y equals mx plus c and we graph that, like this, this point here would actually be 0c, because when x equals 0, the vertical height of that line equals c. In the same way, when f equals 0 here, that term equals 0, and we just get negative w. So in this case, negative w is equal to negative 1.5, therefore w equals 1.5 electron volts. That's how much energy the electrons use just getting off the metal in the first place. Notice this light here, 4 times 10 to the 14, has a fair bit of energy, 4.14, 10 negative 15 times 4. 4 times 10 to the power of 14 multiplied by Planck's constant. It has 1.656 electron volts of energy, this photon here. But it only releases an electron with 0.1 electron volts of energy. So there was a lot of energy that's been effectively not lost. It hasn't been exchanged efficiently for kinetic energy. That is the energy, the difference between the energy of this photon, which was, I said, 1.656, and the energy of this electron. The difference there is the work function. It's around about equal to 1.5. But not exactly, because I've used the real value of Planck's constant, not our experimental value. So the final question we're going to ask is, what is our experimental value of Planck's constant? I've been using the analogy y equals mx plus c. The number in front of x, and x is the variable that's graphed along the horizontal axis, is the gradient. So if we're graphing the energy of the kinetic energy of the electrons on the vertical axis, the frequency on the horizontal axis, the gradient of this line here, this black line, is going to equal Planck's constant. So Planck's constant is equal to the gradient. And finding the gradient is the same as finding the rise over the run. You take 2 points that are on the line. I think I'll take that one and that one there. So the coordinates here are 7.8 times 10, 14, 1.62. And the coordinates here are 5 times 10 to the 14, 0.5. So the gradient is equal to rise, 1.62, take away 0.5, over run. 7.8 times 10 to the 14, take away 5 times 10 to the 14, which is equal to 4, or roundabout, times 10 to the negative 15, and since the vertical is electron volts and the horizontal is seconds to the negative 1, this is electron volts over seconds to the power of negative 1, which is electron volts seconds. And our experimental value is quite close to the real value. So that's hopefully a good explanation of how you can turn a set of results as simple as this into a graph by which you can find the threshold frequency, the work function, and Planck's constant. There's one more question I'd like to try. It's a bit of an easier one. If I eliminate these values here, and actually I can eliminate all these too, and just leave the apparatus there. Say I shone a light, so a photon with a frequency of 7 times 10 to the 14 hertz upon a metal surface, and an electron is ejected. We also know the work function of this metal surface is equal to 2.1 electron volts. Let's figure out the speed of this electron down here. So we know the kinetic energy of the electron is equal to HF take W from this formula up here. We'll find it in electron volts first. So the kinetic energy is equal to 4.14 times 10 neg 15 times 7 times 10 14, take away 2.1, which is equal to I have 0.798 electron volts. Let's turn that into joules. So we multiply by 1.6 times 10 neg 19, and I have 1.277 times 10 neg 19 joules. It's important to go to joules because when you use the next kinetic energy formula, EK equals a half mv squared, if you put electron volts in here, you're going to get the wrong answer. And in fact, you're probably going to get a velocity that's faster than the speed of light. So since we know now the kinetic energy of the electron, EK is equal to a half mv squared. Let's try and get V by itself. 2 EK over m is equal to V squared. So if I take the square root of both sides, I get V. Let's plug in all the values we know. 2 times 1.277 times 10 neg 19 over the mass of the electron is 9.1 times 10 neg 31, that's given. 9.1 times 10 neg 31, all under a square root we have 5.30 times 10 to the 5 meters per second. And this is an example of combining the photoelectric equations with simple energy equations for motion.